Okay. Well, welcome everyone. My name is Katie Poss. I work for Turner Construction and I'm the co-chair of the CLF Nashville Hub alongside Nicole Ritter. I wanted to let everyone know that we are recording today's session and it will be posted to the CLF Nashville YouTube channel later this week. If you aren't familiar with the Carbon Leadership Forum, the CLF at the University of Washington is accelerating the transformation of the building sector to radically reduce the embodied carbon in building materials and construction through collective action. They pioneer research, create resources, foster cross-collaboration, and incubate member-led initiatives to bring embodied carbon emissions of buildings down to zero. I encourage you to visit carbonleadershipforum.org to learn more, and also encourage you to join our Nashville Hub community on LinkedIn. And now I will hand it over to you, Heather Brown.
Thank you, Katie. So we did a session back early in the summer, just introducing different ways to reduce embodied carbon in the building material of concrete. And it was fast and furious. We had 7 or so speakers. So if you haven't seen that, I would encourage you to go back to our YouTube channel and view that. It was an opportunity just to present different strategies in reducing embodied carbon. And the conversation was such that we really wanted to have a second webinar diving into a few projects that have taken advantage of those technologies. And so today is a focus on local and regional case studies involving the different strategies that we presented back in June. So we've got 4 speakers today, and what we're trying to do is really showcase all of the different applications that you can benefit reducing embodied carbon in. So we're going to start with NRMCA, Frank Gordon, and he's going to jump into a wide range of projects related to reducing the carbon footprint. Frank, thanks for coming.
Thank you, Heather. Thank you, Katie. Thank you for allowing me, especially to CLF, for allowing me to be a part of this. I really think that this is great and important work that we need to be doing within the industry, just in the matter of communicating ways that we can definitely be working on embodied carbons and our carbon footprint within the industry. I think we've got a great story to tell, and I'm glad to see that we're using more and more opportunities to do that. So I'm just going to go ahead and jump right in, and I'm going to just talk about, first and foremost, we're going to talk about a webinar that we did a while back called the Top 10 Ways to Reduce Concrete's Carbon Footprint. Now, I'm not going to go through the whole webinar. It's very lengthy. In fact, I'll be providing you at the end of my presentation a web address for YouTube where you can go and see the whole webinar. And if you're ever interested in having it at your companies, having it as a private webinar, please let me know. And that's something that we'll be glad to do for you as well. But I wanted to hit the highlights today so that everybody was aware of the opportunities to learn more about this. And I'm trying to get the screen to advance here, and it doesn't want to. Not sure what's going on. Hold on here. There we go. All right. So the top 10 ways to reduce embodied carbons in concrete. So first one right off the bat is to communicate carbon reduction goals. So what we want to ask you to do is to look at collaborating liberally with your design teams, communicate and specify your goals or targets clearly within your actual documents, whether it's your specifications or your drawings, and then repeat and restate your goals at all pre-bids and pre-construction meetings. So remember, in all ways, communication is key, and this is one of the best ways to ensure that your project is going to be hitting specific target goals for embodied carbon throughout the project, is to make sure that you put this in multiple places, make sure that they're, of course, coordinated, but make sure you're giving opportunities for everyone to learn what targets are you're trying to hit. The second one is to ensure good quality control and assurance. Now, I can't speak enough about them, but one of the things you want to do is to require your producers to adhere to design standards and to avoid the over-design or overuse of cement. Adhere strictly to ACI and ASTM design standards, especially for storing and testing of project samples, and then require your provider plants and personnel to be ACI certified. I can't speak highly enough about that one or emphasize that one enough. It's very important that good controls are put in place, and good QA/QC will allow you to be able to reach the goals that you're trying to reach for your projects. Next is to optimize your concrete volume. Now, by optimizing concrete volume mix designs and volume by using life cycle analysis software and by reducing the use of concrete finishing materials and chemicals, that helps to reduce your concrete's carbon footprint. A lot of people don't realize how much of an impact things like finishing materials, concrete finishes actually add to the embodied carbons in concrete. One of the best ways to do is to do concrete that is finished without any sort of chemical or finished material on top of it. And we get into this a lot deeper in the seminar, but we talk about how being able to allow that concrete to absorb embodied carbons, because we have discovered that concrete can become a carbon sink instead of a carbon source. So we want to make sure that concrete has the ability to absorb as much atmospheric carbon as possible. The next one that you're going to see is to use alternate cements. Now, went ahead one, sorry about that. So use alternate cements. So use cements that are alternates to Portland cement, such as blended cements like PLC or Portland limestone cement. You also know this as ASTM C595 type 1L cement. Now, this helps to reduce the amount of Portland cement in the mix design, thus reducing the mix's carbon footprint as well. The next one that you're going to see also is to use supplementary cementitious materials, also known as SCMs. Nearly all the concrete used today has some sort or amount of supplementary cementitious materials or SCMs in it. So when we continue to look for alternative SCMs, especially from recycled or naturally occurring materials, it also helps to reduce the amount of cement in ready-mix concrete, thus reducing the CO2 introduced into the environment. Next, we want to look at doing admixtures. Now, another simple solution is permitting that all admixtures that meet an ASTM standard and then listing them in your concrete specification, and then making sure that you also list those that potentially don't meet a standard. This would be considered part of your proper submittals and the technical backup for your project. So being able to limit those that don't meet a standard, but then opening it up so that all that can meet the standard can be reviewed and be looked at through the submittal process is another way that you can also reduce your embodied carbons. Next we have, setting targets for carbon footprint. I've always said that it's impossible to hit a target that you don't know exists. And there's also a popular saying that most of you have heard out there that if you aim for nothing, you'll hit it every time. So we want to resist the temptation to set carbon footprint limits for individual classes of concrete, which also in effect, this is the same as providing a prescriptive limit on materials. And it leaves very little room for the contractor or the producers to innovate and help meet the project performance requirements, including budget and schedule. So this is one of the best approaches to use for a whole building life cycle assessment to set a carbon budget for all the concrete in the building. Then number 9 is to sequester carbon dioxide in the concrete. You've heard a lot about this lately. There's a lot of carbon capture type technologies that are out there on the market, but carbonation, which is the process we're talking about, is a naturally occurring process by which CO2 penetrates the surface of the concrete and chemically reacts with cement hydration products, and this helps to form carbonates. Now, theoretically, given enough time and ideal conditions, all the CO2 emitted from calcination would be sequestered via carbonation. And there's a lot of technologies that are available. I'm sure some of that will be hit on later on in the presentations, but there's a lot that are available now on the market to be used. And last but not least, we have encouraging innovation. Now, while considering the most challenging part of these 10 reasons, I apologize for going too far there. You want to encourage innovative thinking. You must maintain control of the process and the protocols used to find mixed designs that reduce embodied carbons, but communicating the carbon reduction goals to the contractors and producers during the design process is very critical. So let them know that you are looking for innovative solutions and ask them to bring opportunities to the table so that they have the ability to have gain ownership in the project and they become a part of your team in being able to reach these goals. And just like the first one that you saw that was communicate carbon reduction goals, encouraging innovation is just also another part of that communication process that will help you to be able to hit these goals. So looking at our case study today, our case study is Park Center, which is in Atlanta, Georgia. The architect is Cooper Carey. And this is a new master plan that was designed for a regional mixed-use campus in Dunwoody, Georgia. State Farm Insurance is actually the major tenant, and this is actually phase one, which is now complete, consisted of an office building and a parking structure with a direct connection to the Dunwoody MARTA station. Phase two will have 2 additional buildings that you can see in the background there. And amenities will include a fitness center, street level restaurant, all the amenities you would expect to find in a mixed use facility. Now, each of these buildings are going to be 20 stories plus, and they were shooting to achieve a LEED Silver certification, but they actually were able to achieve a LEED Gold certification for the project. So the structural engineer was Walter P. Moore, and they specified an aggressive cement replacement for each concrete element of the 20-story plus concrete framed office buildings. So in the drilled piers, also in the columns and in the shear walls, they specified a 56-day strength instead of a 30-day strength. The concrete was also supplied by Thomas Concrete with over a 50% cement replacement that they were able to achieve using a ternary blend of slag and fly ash. And additionally, carbon cure, which is one of the carbon capture technologies that we were referring to, was used in the mix to further reduce the cement by another 7%. So in other parts of the elevated structural frame, with the concrete supplied by, with concrete that was supplied by Argos, another 56-day strength was specified in the columns and the shear walls, and an aggressive cement replacements were achieved for various other elements. So overall, the carbon smart structural concrete strategy saved over 19 million pounds of CO2 emissions, equivalent to not driving over 21 million miles. And that's over 340,000 trips around the I-285 perimeter in Atlanta. This project is now open, and the second phase is looking to open sometime in 2023. So to look at how they achieved this, excuse me, so looking at how they achieved this, they did a whole building life cycle assessment as part of their LEED and sustainable design strategy. This has resulted in structural engineers specifying environmentally impact reduction targets on their drawings, actually. This is an example from Walter P. Moore that you see on the screen, where various environmental impact reductions were specified on the concrete matrix within their drawing set. The targets could then be shown to have been achieved by the environmental product declarations, or EPDs as we know them, that are submitted to the design team. And this is being done on several other projects going on in the Atlanta area, such as Children's Healthcare, the Signia Hotel project, and others. So as you can see, this is very much something that's attainable now. This is not something we're looking at in the future. It's something that's actually being done successfully now. So that's really all the time that I have today. I want to thank you again. Thank you to Heather and to Edie for allowing me to be a part of this today. Sorry it was so quick, but you know, we have a lot of speakers to get to here. If you look there in the middle of the screen under the Build with Strength logo, there is a web address there that tells you how for the Build with Strength website to go to sustainability, and it will actually give you the top 10 ways webinar for you to watch at your leisure. So thank you again for allowing me to be here today. Thank you, Heather and Katie, and I hope that this was valuable to you, and look forward to being a part of others in the future.
Thank you, Frank, very much. So now we're going to transition to some horizontal work and look at heavy highway paving. Mr. Will Gray is with us today from AG Pelts. So I'm going to share his presentation and present Will Gray.
Okay, I hope you all can hear me because I'm traveling, so hopefully this is working.
Yes.
All right, just quickly, a little bit about us. If you're not familiar, we are a roller compacted concrete paving contractor. We work all over the U.S., but mainly in the southeastern states. To date, we've placed over 9 million square yards of RCC pavement, and it'll probably be about the last 20 years or so. And Heather, I'm gonna be on. Okay, thank you. So historically, most of our mix designs were straight cement. We do everything by the dry weight of aggregate. So as a percentage of the dry weight of aggregate, it's 12 to 16%, and that typically correlates to about 400 to 550 pounds of cement per cubic yard. In the recent years, as RCC has become a little bit more advanced, we have started using some supplementary cement type ingredients. And you might have to forward the slide there one. So one of the things that we deal with a lot with is ASR. So in the past 10 years or so, we have started using type FS, and of course the main reason was for ASR mitigation, but that did reduce our cement content. Now, in the past 5 years, we have implemented ternary blends. We've used a lot of slag cement blends, not only for ASR mitigation, but due to economics. And recently, just this year, we have started on our first PLC project. So Lehigh did a great job with ALDOT on getting PLC accepted in DOT mixes. And then they came to us and said, we know that there's some projects coming up that you guys are going to be constructing some shoulders on. So we did some internal investigations, putting up some PLC mixes in conjunction with our normal mixes, and we didn't see any differences in the strengths. And then we placed some test strips just because I wanted to be sure, as this was a pilot project, that we looked like we'd have good surface durability, and all of that came out well in lab results. So we went ahead and we started this PLC project early this year. So, and if you're not familiar, advance please. EcoSim PLC is Lehigh Hanson's product. They do make it near our location in Birmingham, and the project locations are probably like 15 miles from this cement mill. So it's a good fit for everybody. This cement contains 10% more limestone, using the same components as traditional type 1. Some of the benefits that they have promoted and we have seen is that we do get a little bit higher density. Our unit weights of this concrete were probably about 2 pounds per cubic yard higher than our traditional, which is a big thing for us because it actually allowed us to get density a little bit easier than in the field than with the normal type 1. Of course, the big advantage here is it reduces the amount of cement clinker required, so that reduces the energy needed, and therefore our carbon footprint is reduced. The next slide is just a picture sort of our operation out there. So this is a interstate rehab project that we're the prime contractor on. The sort of the scope of work is to repair the interstate. It's a concrete roadway, and then we are replacing the asphalt shoulders with roller compacted concrete. The next slide has some just details about the project. This is the first of two. So we are replacing the inside and outside shoulders. The current project has about 130,000 square yards, and the next project will have about 145,000 square yards. So between those two, I guess this project will utilize about 40,000 cubic yards of concrete, and all of it will be done with Portland limestone cement. Just like most road work, we work a lot at night, so it's varying times of placement, split between day and night to accommodate the traffic flow out on the roadway. As far as a little bit more about the project, the next slide, we set up a portable plant there in the cloverleaf of an interchange on the interstate. So actually, this is a Google Maps photo. So they've taken a photo since we set up, so you can actually see our operation there. So we're self-contained within a cloverleaf right on the project, which reduced our haul time, and energy required for a haul substantially. And then the last shot there is just some pictures of the completed shoulders. So, we are getting great results with this product. We've had exceptional strengths. Most of our strengths on this project have been in the 6,000 PSI range at 28 days. And so through the use of this, and it's a great idea, especially in road work. We've been able to reduce the carbon footprint on this project compared to our typical operations by at least 10%. And I'm unfortunately am not familiar enough to give any data as far as what that does for vehicle emissions compared to vehicle emissions. But if you have any questions about this, of course, you can contact Chris, who's really the expert in this area. I'm just filling in for him today. But his contact information is on the next slide. And I think that about wraps it up, Heather.
Well, thank you, Will. I know you're traveling, so I'll go ahead and open up an opportunity if anybody has any questions about this technology, particularly using it in RCC. Feel free to put it in the chat box or unmute yourself. So Will, did Lehigh help get the DOT approval with Alabama? Were they instrumental in working on that?
They were totally instrumental. They
Okay.
had done all the pre-work prior to this project, and they came, when we were the successful bidder, they came to us with that idea. And of course, I mean, for us, it was an easy decision because we couldn't see any technical reasons why it wouldn't work. And of course, it being a greener product, it was interesting for us. So it was, but most of the legwork was done by Lehigh.
And you foresee using it on future projects potentially?
We have, for us, I mean, we see no, I mean, I'll be open to using it on any project. It's been excellent to work with. We haven't seen, the only thing we've seen is really positives. There's the only negative that I could ever say is that the limestone cement concrete, when you make concrete, seems to stick to rubber a little bit worse than regular concrete. But that's the only, which is not a real drawback. That's the only thing that we've seen different from normal conventional type 1-2 concrete.
Interesting. Okay. Well, if nobody else has any questions, I appreciate you, Will, and I know you want to get on with your day, so thank you for joining us.
Thank you. Thanks for having me.
Okay, wonderful.
All right. Bye-bye.
Bye-bye. All right, so next I have Zach Canterbury and Mike Baldoni, who work with IMI, and they have several case studies to present as they have implemented one of the technologies that we spoke about in our last webinar. So Zach and Mike.
Hi, thanks, Heather. Hi, everybody. Thanks for having us on today. My name is Zach Canterbury with IMI. As Heather said, Mike Baldoni, our QC manager here in the Nashville metro area. He'll be joining me as well. So what are we talking about today? Obviously, we're talking about reducing our carbon footprint in concrete. So there's a few, trying to get control here. Having a little bit of trouble. Here we go. So we're going to get into how to make our concrete mixes a little bit more sustainable. SCMs, which have been talked about already today, is certainly part of that. Carbon Cure, a fairly new product that's been introduced to the market this past 5 to 7 years. We're going to talk about Carbon Cure, how it works, some of the testing and validation that's gone into it, and some case studies of some local projects here in the Middle Tennessee area. Before all of that, though, I'm going to give you a little rundown on IMI. So IMI, we're a building material supplier, founded in 1946 in central Indiana. We've since then grown to encompass Kentucky and Tennessee, and as you can see there, some surrounding states. Here locally in Tennessee, we provide our customers with ready-mix concrete. Sorry, trying to get it going here. Moving on, having some trouble moving on to the next slide. Sorry about this, but moving on to, I guess I'll talk briefly as I'm getting control of the slides here. Perfect. Okay, so we've already talked a little bit about SCMs, or supplementary cementitious materials, but when we're really getting into how to lower the embodied carbon of concrete, from a sustainability standpoint, we need to lower the cement. I'm sure a lot of people on here have already heard or know that Cement is one of the largest greenhouse gas emitters in the construction industry. I think worldwide, it's somewhere around 5 to 7%, depending on the study that you look at. So any way that we can reduce that cement content of our concrete mixes, the better. I won't get into too much detail on SCMs, but products such as fly ash and slag are typical SCMs that are used. Now getting into carbon cure, it handles that in a very similar way in reducing the cement content of a mix. Basically, carbon cure, it takes CO2 at the batching process. We'll introduce it while the concrete is still green or plastic. And what will happen is the CO2 will react with the water and the cement, mineralizing into calcium carbonate. This increases the mix's strength, allowing our quality control team and the design partners on the project optimize the mix to make it greener. Okay, lowering the cement a little bit, which helps it become more sustainable. Now I'm going to take it or give it over to Mike, and he's going to talk about some of the testing and validation, and then get into some of the case studies.
Hey, everybody. Thank you, Zach. Thank you, Heather. Sorry about that. I'm going to speak a little bit about the testing and validation that we had to do for this project and several projects that we're going to talk about here. Obviously, all of our plastic, concrete test results that we had to do anytime we're talking about any of our mix designs, the slump, air, temp obviously was done. We had to take it a little bit farther as far as doing some shrinkage testing for some of these projects, flexural strength testing, as well as compressive strength. And I know we're really honed into the carbon cure technology. We've taken as far as doing durability testing, bleed water testing, everything all around. So kind of just do a quick overview as far as all the results are concerned. Everything seemed either neutral or positive as far as strength, and all the other requirements were done. So really saw some good results and decided to take the plunge and invest a little bit more as far as the carbon cure technology goes. So the first case study that we have, as you guys can see the picture right there, the owner and developer was MDH. The general contractor was FCL Builders. This project was really huge for us because it was kind of the first carbon cure, I'd say, commercial project that we did down here in Tennessee. MDH was pretty well versed and kind of educated on the carbon cure technology, which definitely gave us a leg up. Kind of gave us free range as far as our mix design portion goes. So as you can see to the left, that's us pouring our slab on grade mix. So we were able to kind of optimize and use a blended aggregate mix, which anytime you can get the most out of your aggregate, that will lower your cement content, which essentially lowering the carbon footprint. So able to do that for the slab on grade, and then also able to reduce around 10 to 15 pounds of cement per yard using the carbon cure technology. So had some really good results and feedback from that. And then as you can see to the right there, that's the tilt panel walls that we do. So this project was actually the very first tilt-up panel pour in North America using carbon cure. And then I'll move to the next slide. That's just kind of the bird's eye view, I guess, of the project when it was done. Total was around 15,000 yards total and saving over 300 pounds of CO2 total for the project. So moving on to the next case study, that's the Vanderbilt College Dorms Building B. Had the opportunity to do this with Lithco Contracting. This was kind of one of our first projects that I'd say kind of geared toward the more vertical elevated side of it. So we used carbon cure in all the columns and all the elevated post-tension slabs that were used. It was kind of done during the winter time. So we actually, as bad as it sounds, had to use a straight cement post-tension mix design during the winter. But because we were using the carbon cure technologies, we were able to reduce at least 25 pounds per yard of cement for the whole project. So not only did we get good 28-day results, during these colder months, we were able to achieve 3,000 PSI within 1 to 2 days. So no delays on the schedule or nothing like that. Keeping it going, this is the Havens at the Gulch project. So as you kind of can see there on the bottom, all the concrete used for this project was for a parking garage, but we used post-tension mixed designs as well. This, of course, had to be air entrainment. So, of course, anytime we're dealing with air entrainment, that can be kind of a challenge for us. Not only did we have to meet early and later day strengths, but we had to meet shrinkage requirements as well for this job. So had to do all the testing for that. The elevated slabs for this had to be around 55 to 6,000 PSI, and we had to hit 3,000 PSI within 1 to 2 days. Overall, project-wise, didn't have any issues with any breaks and no issues to the schedule for the contractor. So the next one, as far as yardage goes, this isn't necessarily a huge project. I think overall is around 3,000 to 4,000 yards total. This is a thin, heavy-duty pavement for the Prologis buildings, as you can kind of see in between there. Not only do we have to meet a compressive strength, we also had to meet a flexural strength as well. On top of all of that, we did have to use 4 pounds per yard of macro fibers. So kind of different challenges that hit us, but we were able to reduce our total cement content from around 3 to 5% total. So able to meet all these requirements as well as lowering that carbon footprint as well. So the last case study that we have is the Nashville Yards Tower 2. So this project actually hasn't kicked off yet, but we were able to, as you can see, there's quite a bit of elevated slabs for this project. We got approved and we were using an elevated mix design that reduces 45 to 50% of cement, as well as using carbon cure technologies as well. So the PSI total can range from either 4,000 PSI to 6,000 PSI. So kind of quick overview, I guess, since 2017, we've obviously have invested a lot in carbon cure. These are kind of the statistics that we've gotten kind of year to date. So we did finally reach our 2 million yard mark using carbon cure. And as you can see, that total CO2 savings right there is well over 35 million pounds. So something that we're very proud of and continue to get those numbers higher and higher every day. So, and that's all we got. Katie and Heather, thank you again for having us. And this is our contact information for me and Zach if you guys have any other further questions.
Thank you, Mike, and thank you, Zach. Great projects. And I'm sure there's more to come. There's a lot of big box stores that are looking for carbon reduction solutions. So thank you for being a resource. So we're going to wrap up with Andreas Silvatas, who is the Director of Sustainability with MB Solutions. And we're happy to have him. And he is going to, I think, take over the presentation and present now.
Yep,
Andreas.
thank you very much. Bear with me 1 second. I will share immediately. Can everybody hear me loud and clear, Heather? Can you?
Yes.
Wonderful.
Yes.
All right. While I'm waiting here for the screen to pop up, there you go. So one of the major things for me during my presentations and during my entire career was always to look after the scientific method and to try to see what is going on, not only in concrete, but in everything that we call life. Now, as we see, concrete is changing and we have a lot of challenges in front of us. And the key drivers for the challenges in urban living, as we encounter it today, are being found in the UN Agenda 21 and the UN Agenda 2030. So for those of you familiar with the UN Agenda 21, there will be nothing new, I think, but for those who are not, it is quite some publication and it's worthwhile to read it. Now, based on the findings that the gentlemen and ladies came up with, was that we should look after changing how we live as well as changing how we build. And one of those challenges then that we as an industry were tackled with was, of course, we want to continue to build in a certain pattern with a certain skill set and also timing. So as a matter of fact, whatever we wanted to do needed to contemplate those 3 things on the left. That meant if we are going to change, evolve, alter, the most man-made used material called concrete. We would have to do it, of course, without compromising its engineering properties, and neither, of course, its architectural outcome or the building ability or constructability, as it's also sometimes called, for the contractor. And all of that, as I see it, some people around the world have been trying a lot of things, but pushing hard, didn't take the path of science or the backbone of science, and sometimes this was then misleading in terms of certain criteria and outcome. But for those of you then who have studied the phenomena of different raw materials and understand how they have to be compiled together, there's a bunch of materials that can be used to reduce, if you like, cement. One of them, for example, is fly ash, as you can see, slag, limestone fines, aggregate fines, etc., but also glass powder, and I will have an example of those here shortly. Now, while we are talking about changing and altering our performance, there are also some trends that are coming up in the way that we are trying to build and accommodate then the developers. And one of them that you might see also in Nashville coming soon, or probably being already there, is a higher modulus of elasticity, more rigidity, to be able then to counter any type of acceleration of buildings, etc. You can read the list for yourself, but it's quite some remarkable and desired properties that are out there for us to meet. Now here we see something that it's a very interesting pathway, if you like so. So this is a concrete that has been done with 100% recycled concrete aggregates. So they all came out of old concrete, and this is just to showcase what glass powder here in combination, for example, with fly ash can do. So glass powder, it has the newest ASTM, I think it's 1866, if I'm not mistaken, and it's available around the US. And for me, it's an old material, but I'm happy to see that's now available here in the US as well. It's a phenomenal material, and as you can see, together with recycled concrete aggregates, it delivers a tremendous amount of strength and also durability. If we look into other fashions that unfortunately time-wise I don't have them here, but just for regular concrete, you see that the brakes are phenomenally high, although that concrete was designed to be just the 4,500 psi. So talking about concrete with a lot of replacements, the project that I was involved with when I came over to the United States first was the World Trade Center. And when I presented to them that solution, it was kind of awkward, the looks, because those looks were like, in terms of not believing what was presented to them. But nevertheless, the building is standing and it's very structural sound. So this had already 72% replacement. On the right, you can see some life cycle analysis for not the entire concrete though. This was at that time produced just for the 14,000 psi volume that was then placed for the World Trade Center. But you can see here, if you like to measure the things that we are being told to measure, that's what you get then as values, and you can take them and compare them accordingly. One of the other interesting buildings was the 432 Park Avenue, also 71% replacement, all architectural surface finish white, with the highest engineering requirements ever on the planet on concrete science. And you can scroll around with your eye and take a peek. For now, a standing building with the highest replacement of cement is 99 Church, or the official name is now 30 Park Place, and also this had only 22% cement in the mix. Going forward to the next slide, we see here the next world record. This is 270 Park Avenue. It's right now under construction. The entire building was demolished. And right now, so this was the largest demolition ever in the United States, 52 stories, sorry, double E there. And now we are pushing for the superstructure. 16,000 PSI was required, a low heat of filtration, 3 hours workability time, etc. So now you can see here the concrete, and I will touch on the videos. One thing that is very interesting to follow is that the concrete here breaks actually at 56 days, roughly 24,000 PSI. At 90 days, roughly 26,000 PSI. Water retention is definitely, as the contractor liked it, 3 hours and more, and all in 30 inches of spread. So you left massaging the concrete just to see how it is for everybody. It looks a little bit awkward now at that video. Please wear gloves. I decide personally not to do this so that I can have a better feel for the concrete. This is now fresh from the press. We were asked to help a pre-stressor meet a certain requirement that he was facing. So he was faced with replacing up to 40% cement, and ideally he should use type 1 cement in a pre-stress. So they have, of course, a certain timing, and for them it was essential to have 6,500 PSI at 18 hours. The achievement you can see right down there, it was coming in on Friday. So 7,880 PSI was achieved. Please note this concrete has no accelerating admixture. It is self-compacting, self-leveling, at 31.5 inches of stable slump flow with no silica, and it has 72% replacement of type 1 cement. If you like to talk in GWP numbers, which is the global warming potential, this had the lowest GWP numbers ever seen in a precast pre-stress company around the world. And engineers, DOTs called it unbelievable. So a lot can be done once you understand the structures and the reactions in the nanoscale so that you can manipulate the macro scale. Now let's twist over to Chicago. There was a competition for the lowest carbon solution, and this was won by McHugh, Oremus, and Master Builders Construction. And this solution actually beat the solutions that were presented as well based on steel and or timber, and of course other concrete solutions in the market. So that solution here was by far, for the deciding parties, the lowest GWP numbers, and they were all in all. So the project was then granted to McHugh or Remus, and they will be executing it now, starting either the end of the year or beginning of next year. Another Chicago venue, just because it's right now they are requested in the specs. You see that 65 to 73% was the content of replacement. The priority was to meet the construction needs, meaning timing. So concrete needed to be then stripped, needed to be finished, needed to be post-tensioned, etc., etc. So all those things needed to be, of course, taken into consideration while you're pushing the limits to reach low GWP numbers. And as a side note here, after a life cycle analysis and all those PDs that are necessary then to submit, the GWP numbers submitted then by McHugh were then 14% lower compared to the NRMCA lowest minimum, the lowest requirement of NRMCA for equivalent performance. Now, as I said, those who know me, they know that I'm a scientist to my core, and I never take anything for granted. I will have to check everything for myself. I'm curious, skeptical, but have a lot of life pattern in me, and I will never let anything go unchecked. So as I said in the beginning, for those unfamiliar with the Agenda 21, that's the Agenda 21 here on the top left corner, and you can of course buy it or download it. The words on the right, these are the words that are being used mostly in the Agenda 21. And beneath, that's the template that was used for the Agenda 21. I don't know if people from the 70s remember that book. This was from the Club of Rome, and it talked about the limits of growth. And it talked also about how many people should be on this planet to continue have a certain outcome, etc. So we are all doing those exercises as we know, and we push through it because we are good people and we want to save the planet and we want to do the right thing. So this is here an article, and you see here the front page of the Time magazine, Arctic Meltdown. And I just will read to you one of those things that is common in our days today. The Arctic Ocean is warming up, as you can see on the screen. Icebergs are growing scarce, and in some places, the seals are finding the waters too hot, and polar bears are in danger. Glaciers soon will have entirely disappeared. We need to do something about it now, otherwise there will be no world to cherish in the future. So these are the narratives that I grew up with. I'm from Germany, so this is what I actually dealt with every day. And when I came over, the book, The Inconvenient Truth, was my hero book. So, but then, as I said, take a look at this narrative up there. The Arctic Ocean is warming up, and tell me from when this might be. Is it 2000, 2010, 2020, or is it 1990? Well, I will fast forward here. Usually I give presentations at the university that last 5 hours for that topic, but I think it's important for you guys to see more data so that you can decide for yourself if you want to dig in deeper or not. This is November 2nd, 1922. That's when this article was written. And in that article, you will find out that the scientists and also all the reporters are scared to death that the icebergs are melting and that we will have no icebergs going forward, and that the entire zones around the sea level will be underwater. These were then the challenges in the 90s. These are then the newspapers that we saw in the magazines, and you can take a picture of that. You can read it for yourself. Everything was then global warming and the climate change is coming, and we will just have a few years to live. Now in the 70s, if people remember back in the 70s, and I will be quick with that, so bear with me a second, that is when the big iceberg or the new ice age was coming along. And as you can see here in the newspapers, also here, a lot of strange things happened. The weather was changing, and the weather was changing to the worse because now everything was tuned into surviving the new ice age that is coming. Today, they're using polar bears. In the past, they used armadillos. And as you can see, a warmth, loving armadillo, which expanded its range northward into the American Midwest in the first half of this century, is now retreating southward again. Shift is seen as sign of a cooling downward trend. As a scientist, I have to say that's not a good sign if you have to drill into such an emotional figure, but more or less true data. But keep in mind, this was in 74 and in the 80s. And this was also from that time. I will spare you the limits here, but it was talked about the big freeze. And here, this is what I like. There was a consensus at that time in 61. That consensus was that scientists agree that we are at a turning point and it will get colder. This is from 1912, and bear with me one more slide and then I will be done, just to make you aware that also at that time, cold increased. This is 1912. Remained the coldest winter ever recorded in the United States. Followed by 34, the heat wave, where this heat wave left a lot of farmers with awe because they lost a lot during that time. And it was the hottest time ever. And this, as my last one, 1718, many shops had to close. That the theaters did not open their doors for 3 months. Not a drop of water fell during 6 months. In 1773, the thermometer rose to 118 degrees. And on the right, you can see a nice scientist who showcases what CO2 might do as well. As you can see, the number on the screen that he shows next to the tree is the number that was increased in CO2, because CO2, if you remember how greenhouses are growing their food, the more CO2, the better for the yield and the better for the plants, and more oxygen is produced, et cetera, et cetera. So it's probably interesting to look into this. A little bit to the science, and then I'm done. This is what CO2 actually does. It allows you to find actually an equilibrium. So the more CO2 you put in there doesn't mean that the temperature will rise, because it finds its equilibrium. Read it for yourself. Of course, I will give you all the information that you need. And here's the funny thing. The IPCC itself, the Intergovernmental Panel on Climate Change, says it for itself on 7.2.11. Water vapor feedback is the most important greenhouse gas when it comes to temperatures of this planet. So now you have to ask yourself, why is CO2 the culprit? Because unfortunately, the terms of reference that the IPCC scientists have to follow is only one. They have to make sense out of CO2 and have to neglect any other natural or natural occurring variable. I'll bear you this. This is just all the models that have been produced, and then you have in situ measurements of the troposphere. And all those satellite tropospheric measurements showcase everything else but the model average. My last slide now, and I put this up for food for thought. This is a thought process of Gustave Le Bon from 1700s. He wrote the book, The Crowd, which I highly recommend to everybody to read. The masses have never thirsted after truth. They turn aside from evidence that is not to their taste, preferring to defy error. If error seduces them, whoever can supply them with illusions is easily their master. Whoever attempts to destroy their illusion is always their victim. With this said, thank you for your attention, and I hope you will start to dig into those things, and you will start to acknowledge that there's probably much more out there than politicians want to make us believe. Thank you so much.
Thank you, Andreas. So I've had the pleasure of getting to listen to Andreas several times, and I'd like to say it's very hard to imagine that he just did that in 15 minutes. He can fill a whole day worth of great content. So again, Andreas, thank you for sharing all of your experience with CLF Nashville. So I appreciate everybody's attention. I'm going to turn it over to Katie to close us out, and please look forward to future webinars by this group. So thank you so much. And thank you to the speakers. We really appreciate all of the practical knowledge that you shared today, and all the case studies that are going to help these architects and engineers, specify these types of products in future projects. So thank you.
Thank you everyone so much for your time and for presenting. We do have a couple of minutes for questions. And I'd like to kick it off with a question for any of the speakers. Are there any sort of cutting edge technologies that you're seeing emerging on the market that really have a lot of promise for reducing the environmental impact of concrete? For example, I've seen some companies such as Argos that are looking at an algae-based cement, or a company like Blue Planet that is manufacturing a synthetic aggregate that stores carbon dioxide. Any other technologies, or would any of the speakers like to speak to sort of what's on the leading edge?
If nobody else takes it, I will just dive in. That's Andreas. There's a ton of, as always, if you put a problem out there and you define a problem, there will be always people that will seek solutions. There is concrete that people are starting since years to try to put protein bonds in there. So protein bonds, if you, it is not a biological concrete, if you like, so then, but protein is one substance that once it reacts in a certain way, it also creates a lot of bonds that will allow, for example, also to do some things with less cement. The algae approach is also one. You have tons of other technologies that are out there that would allow, for example, to meet the performances of concrete with lesser cement. I will leave it up to everybody to decide for himself. Everything that I presented here showcase already a tremendous amount of CO2, if you like, so reductions with 72 or 83% replacements. If that is the goal, there are knowledge knowledge tempted approaches where understanding the key raw materials, how they dissolve, how the surfaces actually are being activated, what is activated, what ions are out there. That's already, in my point of view, suffice. Everything else that you can see that can add value to that, of course, is always an engineering potential to bring the material concrete as we know it to a different phase. I, as you've seen, see things differently. For me, cement is not a culprit. It's an ingredient that can be utilized for the liking of the construction method, and as such, I would like to see this going that way, rather than determining something to be a culprit when the data shows something is awkward.
Thank you. Any other questions from the group?
Katie, this is Frank Gordon. I think I just real quickly will speak to, and I appreciate what Andreas had to say and agree wholeheartedly about that cement in and of itself has the potential to, is just another ingredient. It's what we do with it that matters. And I do encourage everyone to, if they get a chance, to go to the Builder Strength website and go under sustainability and watch the top 10 ways to reduce embodied carbon in cement and concrete, that webinar, because it really goes a lot deeper, more than I was able to do in in the time that I had. It really goes a lot deeper into explaining the technologies and the ability to use things like SCMs and other types of technology that are where the envelope is being pushed by our own industry in ways to reduce our embodied carbon. So I just encourage everybody to take a chance to look at that. It's about a little less than a 40-minute webinar. Lionel LeMay is leading it along with Don Thompson. It's very well done. So if you get a chance, look at that. And then, of course, if there's anything I can do from the standpoint of the association, please let me know. I'll be glad to help.
Thank you, Frank. Any other questions?
Hi, this is Nicole. I have one question and we only have a couple minutes, but we've heard concerns about the strength time and the curing time, I guess, of concrete with these strategies. Have you been able to meet the construction schedules with most of these projects?
I will answer that then as well quickly. Yes, 100%, but also exceeded the fundamentals that they had prior to that as a reference point. As an example, the South Bank project in Chicago, that concrete has 73% replacement of cement, and after placement, they are power troweling it within 1.5 hours. Strength, not an issue at all. You can even accelerate the strength pattern, because let me answer it a little bit more than scientific. Cement is an ingredient that, as a particle itself, will start to dissolve. Its ions, which is calcium, aluminum, ferrite, etc., will dissolve into the water. At that point in time, that water will become pore water, as we call it. It will be, in quotes, contaminated with various ions. Those ions actually then try to react, try to find a certain equilibrium, and then try to react to form specific reactions that are more stable than in the ionic strength state that they find in the pore water. With this said, it means that if you can tune and manipulate the system to release, with a little amount of cement that's present, certain ions from all the other particles that you introduce, be it fly ash, be it slag, be it limestone, be it silica fume, whatever it is knowledge that has to come to the game to understand what is being released, under what conditions can I release certain substances to migrate any potential issue and move it or turn it into a potential benefit. And that is what you can do. You can have concrete that has 80% replacement and reaches in 12 hours 5,000 psi. Without accelerators, for example, if you add accelerators, it will go even higher. You can have concrete that's even more cost effective, if you like so, by excluding various things that people deem to be important at that point in time, like silica fume or metakaolin. It's not that they are not important, right? But You can also take them out and save some money if you like so in certain instances, and protect therefore also your vault, but still not negatively impacting the outcome for constructability, be it finishing time, be it broom finishing, be it placing. All of those things that we know today can be met, all of them in the same pattern and even better. It's just as I said, there's knowledge involved. It's not only throwing things together and hoping that with the shear force applied, we will see then the outcome to be perfect. There is more understanding of the raw materials necessary to do this. And I hope I answered your question. I hope. If not, just drill deeper.
You gave me hope at least. What I'm hearing is yes, it's possible.
100%.
Nicole, this is Frank Gordon. Just to specifically answer your question on the Park Center project, it's my understanding that they were reaching 70% at 30 days. They were reaching 70% because of the 56-day curing process. And because of that, they were able to move on up and then continue working and forming up the next level. So from what I understand, the project stayed on time and there weren't any delays because of the extended curing time. So hopefully that gives you a little bit clearer picture there as well. That, you know, I think it comes down to more to construction schedule and just coordination within the GC and the subcontractors. But yes, I believe that, you know, if you have somebody who knows how to look out for that and knows how to, you know, once your initial test cylinders come back in and you're meeting the preliminary strengths, I think that it is possible.
Awesome. Thank you both.
You're welcome.
All right, well, we are at time. Thank you again for calling in, and please stay tuned for our next webinar. It'll be on November 9th, where we will be diving into case studies beyond concrete. So we'll be looking at steel, mass timber, and some interiors materials. Hope you all have a great rest of your week, and we will follow up with the link to the recording. Thank you.